talks, and our first speaker this morning is Weiqiang Wang from the University of Virginia also, and we'll talk about the new categorical, new diagrammatic categorical setting for Schur dualities. Thank you. Can you hear me? Thank you very much. It's a pleasure and honor to speak in this occasion to honor Dan Lacano's birthday. I met Dan first in Santa Cruz, probably 1998. So at that time, I was a postdoc, young as some of the people in the audience. And so many years has passed since then. I'm getting a little older. Now, back then I thought I was younger than Dan, but now Dan looks younger than me. So I certainly wish many more energetic and productive years for Dan. Yeah. And I will talk about Schur duality and some variation of that. And I hope I will present a setting which, in a way, is much more elementary, and in order to go for something higher. All right. Yeah. So let's recall this basic thing for a representation theory conference is a no-brainer, but still, everyone would like to see this to just fixed notation. So you have the classical Schur duality. This is about the double centralizing property of two actions of GON, either group or the algebra, and the symmetric group is D on the tensor space V tensor D. And the enveloping algebra GON factors through to a finite dimensional algebra that's known as Schur algebra, S and D. You can also decompose the V tensor D as a symmetric group representation into the Weiqiang permutation module, as in J.'s talk. That's a view. Then the Schur duality, the double centralized property, you can replace as the Schur algebra is the endomorphism algebra of the Weiqiang permutation module. That's the view useful for our talk today. This related, very well-known combinatorial fact known as RSK correspondence. And in the generalized way, is the generalized permutation. You can parameterize them in terms of non-negative integer matrices. They are in bijection with pi of a semi-standard tableau of the same shape. You will see in last slide a generalization of these RSK. There are many variants, again, by now becomes familiar. And in short, everything in first slide, you can repeat once more, adding a Q in the proper place. But that's not what I want to repeat. One, you can Q deform the Schur duality into a double centralizing action of quantum group. Now the symmetric group is replaced by Hecke algebra type A. So this is known. But adding Q also makes some other things possible. For example, if you view V tensor D as a representation of Hecke algebra, it inherits this Cauchy-Lookup basis of type A. On the other hand, if you view V tensor D as a tensor product representation of a Hopf algebra quantum group, then you have canonical basis. To me, it's a manifestation of Schur duality once more. These two bases coincide. That effect due to Kobanov, Eagle-Frankel, and Keeler. And also, this Schur duality, even at the Q level, has a geometry realization that was discussed in depth yesterday by J.Du. You have seen many amazing formulas, which I will not recall here. Well, the list goes on. And just let me give you one more. And you can upgrade this type A Schur duality to a type B version by enhancing the Hecke algebra action to a type B Hecke algebra action. And since this side now, in order to have a double centralizing property, you need to replace the quantum group by a smaller algebra, apparently. And this smaller algebra nowadays is known as I quantum group. And this U and UI, they form a quantum symmetric pair in the sense of a field. Again, the previous statement, canonical basis and geometry realization, they continue to survive in this generality. Again, I'm going this thing over rather quickly because this is not what I really want to talk about. These are all part of the background. All right. But in the long run, these things will get recycled, will show up beyond this talk. Okay.
PT is not a flower.
It's not. Okay, you mentioned flower. Here you go. So there are many variations. As I said, to explain these slides, it takes more than one lecture. There are many things hidden here. And instead, also I'm getting a little tired by algebra. I want to do something different. And don't get scared. Of course, we have got many wonderful deep talk about triangular tensor categories. And my tensor categories, comparing to them, are elementary. They are diagrammatic. To me, they are like playing a game. Last summer, when I went back to China first time after COVID, I bought a toy from the train station, Lego, for my nephew's daughter. Yeah, you know Lego, you have a few building blocks. Kids can just build some beautiful gadget out of it. And the only thing is there's no constellation there. There's no relation like in some of our algebra you can do. But you can do that in the Tetris game. When you have a full row, they get canceled out. That is some kind of relation you do in algebra. But both things are limited. Tetris, they do not have anything beautiful left afterwards. Okay. And well, our diagrammatic category, I hope to convince you, is a little bit like playing this game, but it's more conceptual and to a certain way simpler. Okay. As with playing games, there are different levels come with it, level of difficulty. We will start with some pretty simple one. When you do monoidal category, what can be simpler than having one generating object, one generating Morrison? All right. Some of these are familiar, I'm sure. They are more expert than me in the audience in the diagrammatic. So bear with me for first 10 minutes. Let's start with Hecke category as a tensor category. Hecke algebra in code, because today you don't see a Q in this talk, but there will be a version, everything, a Q version, what I'm going to talk about. So this tensor category has one generating object, diagrammatically represented by a strand. But now, general tensor project can be represented by tensor product, and diagrammatically, you represent is by n strand. So you have the concatenation horizontally, and the generating Morrison is given by a crossing. And also, of course, you help with identity Morrison. This is just strand connecting to the generating object. So there are two ways to do the concatenation. You can do horizontally, the algebraic structure coming from the vertical concatenation. And the generating Morrison satisfy two simple relations. When you do double crossing, you just string them up. And the other one is kind of familiar Breda relation. You compose three these generating Morrison, three crossings. Okay. That's a simple game you just play. You use this relation to simplify whatever diagram you obtain. For example, m equals 4, you have one of those generating Morrison. I read the things from bottom up. You have one generating Morrison, another one putting here, this is another two. Then you can compose. You see, if you start with 4 endpoints, you always end up with 4 endpoints because that's the nature of the crossing, the generating Morrison. Okay. Then the composing, you obtain a permutation in S4. And you can continue to do that. And the basic fact is now this endomorphism from M strand to M strand becomes an algebra, in our case, over the grand range. I work with either C or you can do with over C. Over C is harder as we go along. In this case, the endomorphism ring of this object M is just the group object symmetric group set. And from this monoidal category viewpoint, if you want to study its representation theory, this is a function from H to the category vector space. You are recovering this direct sum of the module category of symmetric group altogether. And we learned in symmetrical course it's beneficial to study all symmetrical representation altogether. From this viewpoint, there's only one category in front of you. You study just representation of this category. So that is inevitable. And this is closely related to categorization. All the algebra category appear in this talk. They are categorization picture behind it. Okay, let's go up by one level. The same generating object, one generating object. Now I have two generating morphisms. Besides the crossing, I have what I call dot. And they satisfy these two additional relations. Again, look familiar to many of us. This we call the slider relation, how you slide the dot over. It's not quite commutative. You add a lower term, so to speak. This is familiar in this degenerate affine Hecke algebra setting, and that's not surprising. But before going on, let's go back this level two to another level one to look at the baby case. Instead, if you have only one generating morphism dot, no crossing, this is also another model category. If you look at endomorphism algebra, this M strand, I claim this is a polynomial algebra in M variable. You can think the following way. You have three strands here. Now you have a dot, freedom adding any number of dots in any strand, 1, 4, 2, that's what I chose. Algebraically, you can identify with this monomial x1 to 1, x2 to the power 4, and so on. And as a consequence, the endomorphism algebra of M strand in this affine Hecke category is the degenerate affine Hecke algebra introduced by Greenfield. The vector space is identified as a group algebra symmetric group cancel with the polynomial algebra. One way to see this is the following. These are some of the more general diagram you can compose out of the generating morphism. Dot, dot. Now you can play this sliding game, sliding all the dots to the bottom of the strand as much as you can. That's how you obtain the first picture. But they do not completely commute. You cannot slide them freely, then you have some lower term, so to speak. But this is a standard element, one of our basis element, and the claim is all those leading terms, if you write this way, they become linear independent. One reason people consider Hecke category or affine because they have a natural representation given by the category with object like the fixed V vector space somewhere, consider all the possible ends through the tensor. And that connects us back to the Schur duality in the first place. But I brought this obvious in order to raise the following question. Instead of just consider V, keep a tensoring, can we allow some more general tensor factor like wedge square and such? And that's a question raised by Kupperberg a number of years ago, and that gets developed into this Weber category. And originally, it's its own web in the paper Curtis Cummington Morrison, who wrote down a presentation. We do a GO version as follows. Now we change a little bit because now you keep those different wedge A in mind. Our generating object is parametered by A now. They are all positive integer. So they are represented by a strand of thickness A. So these are generating objects. You can do a tensor product. Then object becomes, you write down thickness A, B, C, and such. These are compositions. Okay. The generating morphism, because you have thickness, then you have some natural morphism represented by the merge, split, and crossing, C crossing. they have a bunch of relations which are mostly affine natural. The first one look like you just move the leg B to the other side. This is, if you write down algebraic relation, it already take a while to write this down. That's why diagrammatic is really helpful. Let's not worry too much about the second relation. The simplest case will give you like this. If you compose merge and split, you get a crossing plus a lower term. And because of this, decrossing as generating morphism is not necessary because they can be produced out of merge and split. But it's helpful, and that's a few, and together with one more relation. From this simple relation, you can produce tons of many other relations. And let me just show you. You don't need to memorize, even though it's not hard. Like the second one, we can kind of sliding this line over. That's how you need to read. And also things similar. The first one, you just unfold the crossing. Nothing difficult to remember. Okay. What this really for? That comes to the question we asked about half a year ago. Linliang came to visit me at UVA for this half a year. And I like to know, for even reason going a little beyond the end of the talk, certain high level Schur. And also for the purpose beyond that, I need to have a categorical construction because algebra is too complicated. And then I look around, whether in the literature I can find these things, the high level Schur construction, and I did not. Then I luckily recall a talk by John Brandon last year in NC State. I vaguely remember, John said, Schur is a category, it's just a web category, something like that. Okay, then here we go. So in order to have something I want, I should look at a web. All right, that's why I start presenting this web. Now let's look at this whole picture together. If you think this finite Hecke category, you think a part of the affine Hecke category, and this Hecke is also extended to the web. We are looking for a common generalization here called affine web category. And having these things useful, as we will come back later, Hecke is not just a sub-algebra or sub-category of affine Hecke, it's also quotient. That's the more beneficial viewpoint later on. So we are looking for something, affine web category. And as John and eating of a bunch of other people, they prove this web category indeed is isomorphic to what they call the Schur category, which you can cook up using the isomorphism algebra of direct sum permutation module and such. So this isomorphism you can view is really a categorical formulation of the Schur duality. Okay, that's our new starting point of this talk. And somehow, in order to go to higher, we should go to affine. That is, again, a familiar strategy. And our message is not difficult to get here, but there are some twists along the way, as we will see. All right, I will first give you a presentation of affine web category over C. Yeah. Generating object is the same as a web category. They are just a string of thickness A runs over all positive integer. Generating morphism, they come from two groups, merge splits crossing come from web. And the dot come from the Hecke category. You just put these two things together. The previous one you see, I want to have a common ground between this and this. I'm using their shared generating morphism. Even better or simpler. The relation, we just put those relevant relations together. And this simple definition turns out was not the first one we discovered. We discovered a more complicated one. And when we work and rework, we realize we don't need to do anything if you do work over C. But if you work over integer, you need more work. you cannot just have a dot over a strand of thickness 1. You will need something over thickness A, as we'll see in the next slide. But the point is, this relation you can see over C, you can derive it. All right. Again, let's look at the last relation, for example. In order to come up with this relation, actually, you work out a certain representation on categorical GON module and so on. Out the left-hand side, we call the balloon. This balloon acting something, they always integral, but they always even R vectorial integral module something. And that eventually suggests that there should be a Morrison, you divide out by R vectorial. And over integer, you need that. In order to have a good spanning set later on for the anamorphism of the Hom space. And if you want to have this omega R over R, you can use the first one to define marginal omega R over A victim equal to R. You just put A equal R over here. Yeah. Other relation is just how you move the now seek dot across the seek crossing, and how you move the dot over the merging split. Some of the easiest one is like you can distribute this dot over this seek things leg. Also, they are lower term. Okay. Overall, once you play with this, these relations are still reasonably pretty. Over integer, this is inevitable. All these need to be part of defining relation. Over C, this relation can be derived. Okay, so if you define an algebra or category internal generated relation, there's always certain danger. You get some algebra which is rather simple, like a 0. So in order to make sure that doesn't happen, you want to look at what is the basis for the Hom space. What are the simplest basis Hom space will be Hom space for the generating morphism, like a strand of thickness D. And the non-trivial statement, a priori, this endomorphism algebra is not even known to be commutative. But you can show it's actually a polynomial algebra in D generator. Morally, you should identify this as a ring of symmetric polynomial in D variable. And omega R, omega should read as E. This is essentially you are attaching an elementary symmetric polynomial to this. Elementary symmetric polynomial are good basis over integer for linear symmetric polynomial. So these work over integer. So that's the simplest one. Now for general endomorphism or Hom space, don't get scared yet. This part actually is not so bad. Let's first say something. When you want to look at Hom space between two objects, mu and nu, over a affine web, let's first think about over the usual web. Over the usual web, this is part of the story of the usual Schur duality, Schur algebra. And these people, John Brandon, Ittinghoff, and such, they already identify a basis there with what they call chicken food diagram, like on the left. This chicken food diagram is very simple one. You have a composition, like in the bottom 5, 5, 6, another composition. You connect the legs between them with label of thickness. How these numbers look like, they can be encoded into the non-negative integer matrix. 9, 7 is the 9, 7 here becomes the row sum vector. 5, 5, 6 is the column sum vector. 9, how do you get the 2, 4, 3, 4? From this vertex 9, 2, 3, 4 is the thickness of the leg. They spread out. All right. You can write down such an integer from such a chicken food diagram or vice versa. And this non-negative integer matrix, as we recall, show up in RACSK, correspondence. This is something we're all familiar other than the diagram. Now, our affine version is, this is a reduced chicken food diagram. You add a dot to it in the right place. How do you add a dot? Is all you need to remember is when you have a 1/6 strand, you add the, you are allowed to have this endomorphism algebra has a size of a real symmetric polynomial. You have a basis into this symmetric polynomial. You add those bases. You choose a lower location at every leg. Add those linear symmetric polynomial bases to there, the right place. This is what we call the elementary dot packet. The whole name became too long. I just call it elementary diagram. Elementary stands for elementary symmetric polynomial. So each leg, you attach some the real symmetric polynomial. This case in 2 variable, this one in 3 variable, this one in 3 variable. That's the basis. Back to our earlier question, the affine Hecke algebra or affine Hecke category does not just contain the Hecke as a sub-algebra subcategory. It contains as quotient from this field. It has a minimal quotient known as cyclotomic quotient. And you can ask the same thing. What happened to the web situation? Well, the answer is yes. You can define those quotient category. It's natural called the cyclotomic web category. And then remind yourself, the usual web category is isomorphic to the Schur category. This is a version of Schur duality. And you would like to ask what this cyclotomic web category can be identified. Some experts already have some opinion what they should be. And I thought so too, and I was wrong. And it's not a cyclotomic Schur algebra. So, but it's another plenty thing in the literature. Turns out you can cook up what I now want to call a W Schur category. Those endomorphism algebra, W Schur algebra, that's not the main Blunder pressure of choice. These arise from this higher level Schur duality between finite W algebra and the cyclotomic. It's a very beautiful thing, but a little unexpected. They show up in this way. Yeah. And this itself takes a minute to go on, and I will not continue in this direction. And our original question is actually we were looking for cyclotomic Schur algebra. We just realized when you do some computation here, this Gaussian group, the number simple module is too little. We were at the beginning a little disappointed. We did not find what we want. We realized we need to work a little bit harder. But later on, we realized this one also is pretty in its own way. Can be identified with this W Schur algebra. All right. This notion of higher level Schur algebra in the literature very powerful, useful in categorification, introduced by DJ. Level 2 case also introduced independent by Duje and Scott. And these things were introduced as like a usual Schur algebra. Take a direct sum of permutation module over cyclotomic Hecke algebra and morphism algebra. That is your cyclotomic Schur. It's not even a joint algebra with presentation. All right. And as a part of our question is we will give you a very simple presentation, a diagrammatic presentation, and such and such. That was the original question. And our affine web was our original candidate to produce that, which failed. And turns out what you need to is you need to enlarge this further, what we call affine Schur category. Again, oversee is easier. And for this one, I can only honestly present over C. Over C will have more diagram. Besides of the generating object, which you have seen for the affine web category, the black string with thickness A, now we need a red string labeled by the grand range of field. Besides of the familiar, this generating morphism merge split crossing dot, we will need 2 new ones involving the red object and the relation 3 new family involving the red object. they are surprisingly simple, again, to the expert or to someone who work alone. If you think of cyclotomic polynomial, something is, I don't even have anything beyond linear relation. All right, nothing. And I need two string, two crossing mixed color. I don't have a good name for this. For me, it's this red string is like a wall. I'm read things from the bottom up, so I'm seeing things moving across the wall is going up. I call it up. The other one, for the same reason, I'm going lower. To the left-hand side is lower. So these still, their level coming up. I need a better name. Some of your native speaker can help later. All right. And the relation is extremely simple. Like 19, you can memorize no time. You just move the slide string, the red string over. And this one is also not unfamiliar. You have a lower term. And this is some very simple correlation. Out of such a simple relation, I try to say there are some very nice algebra arise from this picture. Well, the first thing is on this affine level, let me also present a basis theorem. The base theorem for this affine Schur category is not that much different from the affine web category, except now our object of going back becomes multi-composition instead composition. How you want to think about this red? They are string here, but my string now gets shrink to a comma. This red comma is part of the object now. Okay, really that's the beauty. And you have this multi-composition. It's just the old composition. They are separated by a bunch of red comma. And those red comma, you need a red string to connect them. So it's our older, this elementary diagram you are already seeing in the affine web category. You just add a suitable red comma there, connecting them in a red string. But this connecting them, you see, of course, you can connect different way. These two diagrammatic, they are not equal. But because of our relation, they are equal model lower term. That's because this is the only relation has a lower term. And even from this relation, I did not even put down how you move the dot to slide over the mixed color. It can be derived from this. Actually, you can slide over without any lower term. Anyway, this one, so I just pick one representative, fix one representative for each such I call ornamentation. I think I need a better word for this. I'm putting a red color, red line on top of the older one. And I claim that's it. There are many ways you can read. Algebraically, I'm rewriting the older integer matrix into a block matrix, depending on where I put this red string. In this example, I only have one red string. Because the older 1 by 1 block matrix becomes 2 by 2 block. Okay, if I have more, you add more block to it. And that's it. And the corresponding partition attached to it. Now let's go to the cyclotomic quotient, which in some way was our original motivation somewhere here. You can define this as a quotient category. You fix a tuple of scalar. That's the same as some you are familiar with when you talk about cyclotomic Hecke algebra, cyclotomic Schur algebra. You associate with a polynomial. That's the same data. All right. I don't need to write a polynomial. I just write a factor. And this one, the quotient relation is also pretty easy. In a way, you have the first red string. You just do not allow any of the black string go across the first left to the left. Any of those things you just kill it. That's the quotient. And so the object is just you just fix to be you put only choose this now. This L red string there, so they are given by L multi-composition. You once you fix this U1, U2, UL, you are fixing those labels for the red string as well. And from this, you pick the corresponding endomorphism algebra, which of course by definition directs on the Hom space. That is a finite dimensional algebraic line. And the theorem says that coincides with the DGM cyclotomic Schur algebra. And this one, the right-hand side was defined in terms of this endomorphism algebra directs on permutation algebra. So the left-hand side, we give you a presentation. Will be too much to get into a detail here. I want to present some basic theorem for this cyclotomic Schur category. And turns out in this case, some interesting combinatorial thing. This Hom space for the cyclotomic Schur is finite dimensional now if you work over field. Otherwise, it's finite rank over a ring. We work over any ring. We have a basic theorem. This theorem, what we call the double ACST basis, they are parameterized by a pair of semi-standard. This semi-standard table, you can still draw a corresponding chicken foot diagram. But you have two of them, you stack them on top, one on top of another. One is upside. And that obtain a new diagram, which is not a reduced chicken foot diagram. As in the L equal 1 case, that was a construction already in John's paper with his clause. Again, this is a high-level generalization. So the underlying parameterization of this basis is purely combinatorial, and which is something fairly familiar. We have another basis. This is the basis, some version you have seen it before in terms of this chicken foot diagram, and enhanced by partition by lots of these black dots somewhere. Now because in this we are working with this cyclotomic level, L level, I need to put constraint on what partition you can impose for those symmetric polynomials. Turns out, in the old days, I only for this like a label 4 here, each partition has to have part less than equal to 4. But now I need to restrict the length in terms of this level. Now this is a level 2 case example. I write this as 2 by 2 block matrix. For the first hook, the partition you have length 0. That means you have no partition, you need to add it in the first hook. In the next hook, in my case, only 1 case, you can add a partition of length at most 1. If you have more level, next level hook, you will have partition of length at most 2, 3, up to L minus 1.
So we can also give it this definition of the level.
AO is this L. The factor U I have it's L type of scalar. And you can write this as a polynomial with those UI as eigenvalue. That L is referred to as a level for the cyclotomic Schur or cyclotomic type algebra. They are categorized in terms of level L integral module of corresponding affine cosmology algebra. So that's how these things are connected. So I need to put a constraint. So each partition you can put in on each leg is finite many, or has to sit inside one particular rectangle, a particular size. That's the condition. And this is the basis you are obtaining. So linear algebra, you have the same vector space with 2 bases, and these 2 bases, they parameterized by 2 different sets. What can you conclude? These 2 sets have same cardinality. Well, I need to ask a little bit more. I think they should be a very beautiful bijection here, which is still unknown to us. And both sets, as I said, the left-hand side, once A is bigger than 1, you need to add this enhanced by partition, a certain size. And the right-hand side completely classical. this in this L multipartition world, you have this semi-stand tableau, and you have a semi-stand tableau of the same shape. Of course, here you could remove a mu nil altogether. This is given by the content and so on. You can reformulate this bijection just in terms of the really partition intense integer matrix. Yeah. And I think this should have a good answer. Thank you. Happy birthday. Questions? Get your microphone.
You said these things are isomorphic to the DKM construction. So if you use that setting of basis, does it correspond to your basis?
A beautiful question. Thank you for that. Turns out this double ACST basis, what we want to call the triangular basis. It fits into this weakly triangular category, triangle basis setting very well. Some of these or giving some short talk before. This basis is correspond to cellular basis of the teacher. Yeah.
One more question. So your kind of red line diagrammatics feels a bit like what Webster has, right? But he has this presentation for something Marita equivalent to essentially cyclotomic Schur algebras, but then also have this extra weighting thing, so you can kind of get different kind of Fox space realization, this sort of picture, you know, you can tweak things in a way to capture all of that stuff as well.
Since we were kind of long, Webster did not have a presentation. He defined things, those premature out of some value things. These are all in terms of algebra in acting on some polynomial representation or something. And so I'm hoping, well, since you are asking the question, yes, like all those commercial games, we also are ready to produce more variants of this. But not just these things are already, our strategy is already, not just strategy, even we have essentially the recipe tells you how to write down this new category already. This things already work from our way of thinking, we already can match with everything in the literature. And the question you asked is probably on this blue line, green line graded version, type A somewhere. I think we expect our construction will lead to a diagrammatic category, and which is really have a presentation, and it will give a presentation for the including the premature algebra.
So, like you said earlier, the ordinary web category is a presentation for the web category of representation here and generated by the fundamental representations. Is there a similar interpretation for the affine web category?
For the affine,
Is there a similar interpretation for the affine web category? Does it correspond to something in the representation theory?
well, affine category, usually you want to factor through those different cyclotomic quotient. As I said, that is you replace the GLN by the W algebra. That's the answer there. So that line, of course, I did not expand, but you could talk that for half an hour easily. So the W algebra is like for GLN, has additional data, is a nilpotent country class, nilpotent matrix attached to it, E. If that E is 0, the W algebra is just absolute algebra G of n. So you are back to your picture. So when, yeah, so.
If you want the actual full affine web category, it has a representation to endofunctors, which is on the model. So instead of taking the model, we can use a functor by tensor. We use a categorical.
That's also true. We need that action in order to prove our basic theorem.
You know when the paper will be up on Sorry, I will read the paper, but do you know when the paper will be up on the archive? Roughly?
It's easier to prove my conjecture than answering that question. Well, we have two files, each one 40 pages something. We can coordinate these two files that might take a little time. The first one is basically ready, so yeah.
And so can you say a few more words about the triangular basis? It's kind of not obvious to me what the triangular basis is.
Yeah, well, you should go back to John. Again, I pick up from the top. Yes, but they did not. This is a co-determinant basis of a grain. And you should look up that paper of John to see a little more historical remark. Once you, anyway, I declare this double ACT basis, it's a triangular basis. You have a lot of things come free. You basically classify the simple module, they are paired by multiplication. All these things is for us, it's just corollary, you just write down. This is a high weight category and such and such. This is the power of the triangular basis. Yeah, and even for more general case, the triangular basis thing, phenomenon will return again and again. That's why one reason we can do representation theory, even for those more general version of this web or Schur category.
So for this web and Schur category, they consider it as like a low algebra, you consider the module movements that form the high state category.
Yeah, what this one is, you don't need anything fancy. This is a finite dimensional algebra. In this economic case, the anamorphism algebra. So this is a finite dimensional algebra. Yeah, but of course, when you do OSP version, you have copycat. This statement no longer true. But this kind of triangle basis things will come along. More like the neo blower you were talking.
Let us say the last of the questions for later on. Thanks.